Okay. Give me a second as I get carried away with my lectures and keep going. Sometimes I start working on my work and then I get carried away, and before I know it, the class time has started. So let me set myself up for this. You want to quit the kernel? I want to quit the kernel. And share my screen. There it is. Hello. Okay. Now you're all seeing me. Let's carry this to another screen. I will be there in just a second. And you can all hear me. That is great. It doesn't fit into my screen. All right, so let's see where we were and what we're going to do today. Some interesting stuff, which also means that I am starting to set up the final assignment with this GAs. So I'm going to introduce some new materials to be able to complete the tutorials. So tutorials, we are in tutorial 12. Let me go to tutorial 12. All right. So this is what we started doing, and I hope let me quit the kernel. No, kernel is not running. So if you remember, we have been going through the steps of genetic algorithm to really understand what those operations meant in terms of their usage, and we were doing these step by step, and the step that we were at. Let me see if I can find it. This is the entire tutorial. This is the latest form of the tutorial. This is not posted yet. I'll post the first version at the end of today, so that you can start going through it. And we did the traditional opposition versus GA, genetic coding. How much of this we've done? Let's start the beginning. First of all, are there any questions about the previous material that we covered? I am taking that to mean there are no questions. That is there. Let me see what else we have. Evaluation, cells. No, don't evaluate cells. Windows. Okay. All right. We have the. We need the laminate GA, which is my little genetic algorithm subroutine. So let me run that all code. So that's the GA as it is today, with initialization commands and some of the operators, and how to run the GA. We're going to come to those step by step. We showed what the traditional optimization versus GA, how it produces progresses through the design step. I believe we started defining the genetic coding for binary coding, which is the 0, 1. And how much of this have we done? That I am not 100% sure. Were we in the beginning of this, or did we complete this coding of the binary design variables? Did I show you the design space for? I did, yes. We set up a design binary population. But nevertheless, let me go through this. I remember showing the design space. So this is one design variable. It can be represented in base form. You can assign that to dx1. Decode binary GA, decodes this thing into a number. So that's in the case of 100011 is 35. If I define two more design variables, x2 and x3, and code them, there'll be 3 ones and 1010, but their lengths are different. And if I decode that last or this digit, it goes to 63. If I decode these, they go to this, and they correspond to 7 and 10 as defined above. If I want to make a design, I join them together, make one big string. If I take a portion of it, I can take individual design variables 7. So let's take the design 1. If I have actually a longer string with each design variable having a length 6, this will generate the real numbers or integer numbers corresponding to the entire coding. This string, design 1, has 3 design variables: design variable 1, design variable 2, and design variable 3. So each of those defined. So we're switching the problem to a 2 design variable case, and we're representing each variable with 4 digits. And then we use random number generator to create a second design. Let's say it's this one. And if I decode this design, it is generated randomly. It produces an integer, our engineering values of 2 and 12. And I can again define another design, which is the largest that you can have by putting all of them to -1. And if I decode this one, it's 15 by 15. If I make population size to be 10 and use my initial pop algorithm, this generates 10 designs with 2 design variables. Each design variable has a length of 4 digits of binary numbers. And if I decode all of those, or just one of them, the 10th one or the first one, I get the real value. And if I want to decode the entire population, I map the decode binary GA, make a pure function out of it by putting an ampersand at the end. If you haven't learned this is important. This is mapping this function decode binary GA, which is used here for one string here, over the entire population of binary pop. And this will create the points that were generated randomly. Alternatively, I say this function decode GA, instead of mapping, I can actually also put the p size here as the third argument, and it will do exactly the same thing. But this is not the case in case of lambda. So this form and this form are identical. The reason for that is if you look at decode binary GA, question mark decode binary GA, it says it takes a binary list if the call has a second argument, a binary list, and the SNG size, single design variable size, which is integer, then it does something else. If it has three variables, input arguments, which third one is the population size, then it operates on the entire population. So because binary GA is a built-in function that can take three arguments, and the third argument is p size, which is what this map does. Okay, so this is where we left. Now we're going to go to the GA case. For the genetic algorithms for discrete material selection. Oh, now I remember we did this. So I can skip that one. And the third one is the laminate design. Now, we kind of did this, but I expanded that a bit since the last time by making it easier to use some features of this coding. So in the case of laminates, we're going to use still integers to represent ply orientations, not number of plies, not anything else. The stacking sequence will be defined for laminates, but we're going to create an alphabet of integer digits, 1 through 9. We're not using zeros, and we're not using anything 10 or larger. It has to be single. It doesn't have to be ordered list, but laminate alphabet, I can say, I'm going to use an alphabet 1, 2, and 3. Okay, and I store this information in a label called laminate alphabet. So my laminate alphabet is 1s and 2s and 3s, not 0, 1, not binary anymore. If I wanted to use 4 different orientation angles, I could have added here comma 4. That would be 4 different orientation angles in the laminate. So a design will be a complete laminate that we're going to be defining. Okay. Now the size of this laminate that we'll be building will depend on how many plies of these orientation angles that we want to use. So let's say I have an individual design, and you can read these later on. And I'm saying, oh, let's, for the sake of simplicity, use 1, 2, and 3 to represent a stack of 2 0-degree plies, represented by 1, plus minus 45s, represented by 2, and 2 layers of 90, represented by 3. So if I want to represent a laminate that has this many layers and orientations of 2 of these, this would be 490s total. Okay, 92, which will be a stack of 2 90s, stack of 2, which will be represented by 3, digit 3, and a plus minus 45, which is represented by 2, which is this one, and a stack of 2 layer of zeros. So a total of 4, which means I put 1 and 1 in here. 1 means 2 stacks of zeros. 2 of those side by side will mean 4 stacks of zeros. And then another plus minus 45, which is another 2. Okay, so this individual laminate is basically this one. And if I execute that, for some reason I executed everything in the beginning, so it's still showing something. It will give me this laminate. Now, we know that the GAs work with a population of designs. So it's not one design, but I'll have to have a population of random designs. And the size of this dictates, in my case, how many total layers I have. And if I'm using symmetry and balance condition is automatically satisfied by my definition of 0 to plus minus 45 and 90. So plus 45 and minus 45 cannot come together. They have to come as balanced. That's why digit 2 represents plus 45 and minus 45 together. And then I'm also representing with two layers of zeros and 2 layers of 9s. This is not necessary, but in the coding that we're going to be demonstrating, it is built in such a way that it does not deal with changing laminate thickness. If I do this, my laminate thickness will never be changing. There is no zeros in there, so there's no empty pi. And there are only 1s and 2s and 3s, which is 2 zeros, 2 45s, and 2 90s. And this one has 2 of 2 zeros. So the stacking sequence for this is 20 layers total. Okay? So if you count this 2 here, and then 4 more, 6, 8, 12. So that will be what? I counted 12. That's 24. Why do I have 0, 2 plus 45? I'm counting 20 layers. That's 2 layers, 4 layers. That's 6, 8, 9, 10. Okay, that's 10 layers here. There are a total of 10 layers here. So symmetry makes it 20 layers. So this laminate has only 20 layers thick. Now, initial population is supposed to give me now a bunch of designs randomly created beyond this just one individual laminate, one design. So I look at what initial pop does. Init pop creates an initial population of random designs using the population size of P size and a string size of C size, or the length of this, okay? And the alphabet that I define. My alphabet has only 1, 2, and 3s. So this, if I call this function now, by defining my laminate alphabet, which is 1, 2, 3, and if I define the P size and C size of, I didn't define them here yet, but let me see if they are defined earlier. P size is 10, okay. I defined a population of 10. C size for this case is not defined yet. So I'm going to define that to be, say, 5. And if I call my initial population P size, DV size, I'll change it with C size, and laminate alphabet, it will create a population of 10 designs, each of which is a laminate made of 2 layers of zeros, 2 layers of, it's randomly ordered. Stacking sequence changes from one laminate here to another. So if I want to look at this first design, 2 zeros, and then plus minus 45, 2 90s, another 2 zeros, and a plus minus 45. This is actually almost like my initial design, except the zeros are not repeated twice. So it's a different, each of these is a different design. We didn't decode them yet. To do the decoding, I came up with a new construction, which exists in mathematics called association. Okay? It's actually construct a association list of keys and values. Okay? Association, if you define it like this, it has a key and it has a value. So the way to do it is my laminate, my 1 is associated with 2 zeros, okay? My 45, my integer 2 was associated with plus minus 45, and my digit 3 was associated with 90 and 90 stack. So my laminate association, I create a map thread of associations between my laminate alphabet, which is 1, 2, 3, and this stack that I define here. So the output of this is the following. That says, if you have a 1, it will be associated with 0, 0. If you have a 2, it will be meaning plus 45 minus 45. If you have a 3, it will have 90 and 90. Now, advantage of this is if you one day decide to use one layer of 0, which brings additional complications, but nevertheless, if you want to use 1 to represent a single layer of 0, and 2 represents a balanced layer of plus 45 and a minus 45, and a 3 representing only one layer of 90, then this will be your association. Your computations will go with strings that will have this kind of a thing. If I want to change my alphabet to separate the plus 45s and minus 45 without caring about the balanced condition, so I make 1, 2, 3, 4. Alphabet is now 4, 1 through 4. And I make the one to be associated with 0, 2 associated with 45, 3 associated with minus 45, and 4 associated with 90. This will become my association, which will tie integer 1 to a single layer of 0, integer 2 to a single layer of 45, integer 3 to a single layer of minus 45, and integer 4 to a single layer of 9-degree layer. So it brings some additional flexibility in terms of coding your limits. If you want to, say, use stacks of quasi-isotropic, let's say then I decide that 1 will be a quasi-isotropic stacking sequence, and 2, 3, and 4 will be something else. I can basically put here 0, plus 45, minus 45, 90. So 1 will bring this entire quasi-isotropic stacking sequence in there. 2 in this case will bring additional 45. If you want, I can reduce this again to 1, 2, 3 and make this to be plus minus 45. So only 2 stacks of plus minus 45 and 3 being the 90. Then 1 will be, oops, there should be comma in here. 1 will be 0 plus minus 45, 90. 2 will be plus minus 45, 3 will be 90. So you'll be shuffling stacks of layers through the thickness. Okay? Quite a flexibility in terms of design capability. Let's go back to our original problem of 1, 2, 3 representing 2 zeros, which in this case 0, 0, plus minus 45 and 90, 90. So this is my laminate association. And laminate association 1 is basically 0, 0. There's a way to extract the entire laminate out of this. You can map the laminate association, make a pure function out of it, and map it over individual laminate, which my individual laminate was three, 2, 1, 1, 2, and execute that. I get, for this design, 2 layers of 90s corresponding to 3, plus minus 45 corresponding to 2, and 2 zeros corresponding to 1, and 2 zeros corresponding to another one, and plus minus 45 corresponding to 2. And this didn't know anything about symmetry of laminate. Okay, but I actually, out of something similar, wrote another decode GA function for laminates. And this decode GA takes a design, which is a chromosome, and takes the association, which is defined as association. And if you note that its type has to be association, this association has a very specific construct that it has been recognized as association type. And then there's an optional argument, T, meaning total laminate as default. It decodes an integer chromosome into a laminate string using association as such. And the optional argument as a default is T. If your laminate is to be symmetric type, then the optional argument is set to a quotation S. So if I take this individual laminate, which was this, and use this construction, I get now a symmetric laminate, since I define the option to be S. If I do not use the optional argument, then I get half of it. This is the total laminate decoding. It assumes that this individual laminate is the total laminate representation. Okay? If I want to make it symmetric, I put an optional argument S, which is not going to work because this has to be a text S representing symmetric. Okay? So this is now, this coding represents a symmetric laminate, and the axis of symmetry is right here. This is half of it. This is the negative half of it, or mirror image of the top part of it. Okay. And now we also know that the GA has to work with the population of designs. So if I want to make a population of 1, 2, 3, 4 designs, each represented by a stacking sequence of this form. These are not randomly generated, but it's actually generated by defining them. Now I can decode that entire thing into my stacking sequence of a symmetric laminate. Now this is, in this case, only 16-ply laminate symmetric, mid-plane symmetric, so it has 16 different orientation angles, being the mid-plane symmetry axis being this. So I need to do this initial population randomly, and I don't know why I have it twice here. And initial population, if I take that 20 designs of the population and 6 digits each, I will create initial population randomly of 20 designs, 20 layups, 20 laminates. Okay? And these 20 laminates will have 1s and 2s and 3s following the laminate alphabet, and each has only 6 stacks in them. That's the 6 represented here. And if I want to decode this initial layup and put it in here, this is my entire population of laminates. There are 20 different laminates in here. Each has different properties, different A matrices, different B matrices, different Psi-Wu criteria, different stiffnesses, different vibration frequencies. Nevertheless, each design as a population, and when I use something as an objective function, it will understand. We will have to compute the appropriate quantity for each laminate. Okay? Now that's the fitness evaluation part. I think we actually came to fitness evaluation part in the binary coding case. So I defined a function which is this function of two design variable dv1 and dv2. I made the contours of this, and if I create an initial population of design variable size 4 digits along its length, two design variables, 20 designs, and use init binary population to randomly generate a binary. This is not laminate, this is binary problem. It's a continuous problem as opposed to the laminate optimization, which is completely discrete. Okay, well, continuous in the sense of continuous integer variables. You can't have non-integer variables in here. That is going to require another coding that you can ask Benjamin how to do it. He by now is probably an expert on that. Benjamin, are you there, and are you an expert now? Benjamin is there. He says somewhat. Okay. All right. Real numbers are different to implement. I'll have to create another program section called init real. Easier in MATLAB than Mathematica. Oh, you're dreaming. No. Okay, I believe you, but I bet that you cannot do everything that I can do with Mathematica. All right, let's not argue. I have something messages here that I don't understand, but. Anyways. All right. So I need to decode these, and I map the decode binary GA over the entire population. These are the decoded variables corresponding to these, and each has two pairs of design variables. So first design corresponds to 10 and 15, etc., etc. And I can make a plot of these points and show it together with my contour lines for my objective function, which the objective function had multiple thingies like this, and mapped over it. This is my initial population. If you want to see randomly different populations created, each time I run this, I create a different initial population. This will be my starting point. This is not executing GA. This is just randomly generated 20 points that are thrown into the first population. And if I'm successful, these things are going to start evolving and converging to some of the maximum that is defined in here. So my decoded variables were basically these. So if you look at this, for example, 4 and 2, 4 is here, 2 is here, that's this design, that's the first design. Second design, 12 and 6, I'll come here, I go to 6, that's this design here. Third design is 12 and 3, 12 and 3 is this design. Fourth design, 9 and 0, that's 9 and 0 right here. So each one of these is a point in this design space. And each has a fitness value, depending on where they are. if I look at them, these are the fitness values of design variable, design 1, 4,2 as 101. That's this. That's pretty high. Second design is 33. That's 12 and 6. 12 and 6. That's here. It has a value of 33. And third design, where is the largest one? This is pretty large, 321, which is 1, 2, 3, 4. Oh, this one is 400. So it's 1, 2, 3, 4, fifth design. 1, 2, 3, 4, fifth design is 416, which is actually 9 and 0, which is here. So this has the largest value. So obviously these are the minimums, and the largest ones are those. So if I were to make that to be a minus, then my peaks will be here. Right now the peaks these are the valleys. This is a potential peak, and there is a design there which is 9 and 6. And 9 and 6, where is it? 9 and 6. 9 and 6 is this design. So 16th design, and 16th design, 19 has a value of 150. So that's also fairly high. So this is a peak. These are minimums. If I make it minus, then I'll be seeking this one and this one and this one as the peaks. All right. Now, how do I do this in the case of laminate coding? So how do I evaluate a fitness function? This is what you will be needing for your next assignment. So I'm going to have to load composites into this. Right now it's missing, so let me open composites and run that as well. CLT, and so I'm actually a second module that I'm loading to understand the composite commands. So these are my composite commands. And guess what this problem is? It has the same thing as your second assignment, second test. I have this material. I have plastic thickness of 0.3, invariant material properties, strength properties fixed. Q matrix is also independent of the orientation angle, so I'm going to store the Q matrix in this. And I didn't print any of those, they're suppressed. I'm going to use an alphabet of 2. And I'm going to create a laminate association that one will represent 2 degree plies of stack of 2 0 degree plies, and 2 will represent a stack of plus minus 60 degree plies. And I'm going to create design variable size. One design will be 6 digits long, so it will be random combination of 1s and 2s, but total of length 6. There are 2 design variables, which is either 1 or 2, either 2 zeros or 2 plus minus 60s, and population size of 20. Okay? So let's create an initial population of 20 designs using an alphabet of 1 and 2s, and these are my 20 designs, which is composed of zeros and plus minus 60s. Now, if I want to see what these limits are, I'm going to use decode GA and send my laminate association. And I'm going to make these to be symmetric laminates. I don't have to make them symmetric. If I make them symmetric, I'm going to be increasing the size of the laminate definition. And since this is originally actually not a stacking sequence design, it actually originally was an in-plane design, okay? There's no bending in this. So I can only define the hefted laminate, or I can use the total laminate. It doesn't make any difference for me. But for the sake of argument, I'm going to use a symmetric laminate. And I'm going to take this initial population and decode it. And these are my 20 different layups, laminates, which is composed of some random combination of 2 stack of zeros and a stack of plus minus 6 degree plies. Okay? Now, what will I need to actually do something with these stacking sequences? I need to compute either the A matrix or the B matrix or the D matrix for this. And then from those, I can compute some stiffness property or some stress property or strain property, whatever I need. All that information is in here. So all I have to write is a function that will take this laminate descriptions and compute what I want. That's going to be my objective function. Okay? And I'm going to build that step by step so that you can really understand what I am doing here and do something similar for your problem. So I'm going to take my loads are also defined. An X bar for this case was defined. And load cases, there are 3 load cases I defined. Load case 1, load case 3, load case 3, which define alpha and beta combinations. So I execute this one as well. My first objective function, I say, okay, let's not rush, but take each of these laminates, compute the A matrix. So FOBJ1 is taking, I'm writing a new module here for computing objective function. And this module takes an argument of a design, which is a single design, one of these designs in the decoded population, and computes the A matrix from it by calling the A matrix subroutine of the composites, putting the design here, and U vector and ply are external to this function, so it will take U vector and ply thickness from before. So this is already defined, and ply thickness is already defined. And it's going to call the A matrix here with this design that I'm passing on to as an argument, and compute A matrix, which is internal to this function. If I execute this and take my initial laminate was my list of all my designs, and take the first one, that's the first one, and send it to my objective function calculation. That's the A matrix for the first layup. If I want to see the A matrix for all the layups, then I would have said map FOBJ1, and it only takes one argument, so I don't have to actually create a pure function. This will be the A matrices of all the layups in there. Now you're going to see something funny in there. What is funny? There are 20 designs, but I don't have 20 different laminates, 20 different A matrices in here. Why is that? Question to everybody. I had 20 different designs in here. Okay? And I evaluate the A matrix of all of those here, but I don't see 20 different A matrices. The first 3 A matrices are the same. And this one is also same as the previous one. This one also same as the previous ones. This one also has the same as the previous ones. And then there's a matrix start with this. And this is also repeated here, and here, and here, and here, and here, and here. What's happening? That is correct. The A matrix depends only on the number of unique ply orientations. Although stacking sequence is different between the first design here and the second design, apparently if you count the number of 60s and the number of zeros in there, they're identical between the first design and the second design. Therefore, its A matrix is same between first design and second design. And the third design. Okay? So they don't have to be exactly the same, the entire laminate stacking sequence. As long as the number of layers of a given orientation angle is the same, you get the same A matrix. Okay. But I can't use this A matrix as an objective function. I can probably use A11 as an objective function. Okay? If my A11 was my objective function, then I could have defined my FOBJ differently and say that, okay, oops, come on, 1, 1, A11. So my objective function will only compute the, spit out the A11 value. That's A11. And if I map it over the entire laminates, this is the A11 of each design. Again, 1, 2, 3 designs, first 3 designs have the same A11, and it's a single number. If I want to maximize by A11, I can use this objective function right away. But I'm going to make it more complicated. I'm going to make my objective function to be a Saiwu number, which means I need to change my objective function definition. And I create a second objective function. I copied the one from above as is. And instead of ending it here, let me copy it. I'll show you what exactly I did. This was my objective function 1. I added to this another internal variable that I called midplane strains. And then I put a column here and computed my midplane strains from loads, load n, by multiplying it with the inverse of A matrix. So I computed A matrix, then I computed midplane strains by using the inverse of the A matrix here, with the load n coming from external to this subroutine. So I created the second objective function that now computes midplane strains. And if I take the first design and evaluate it by using my second objective function FOBJ2, these will be the midplane strains. But it's in terms of alpha. And I don't want any symbols to appear there in my output. So what I do is I also modify this too by adding another argument, load case, and then put that load case as an evaluation to the previous function. I redefine my FOBJ2 for different load cases. So now, if I call my objective function with load case 1, these are my midplane strains. If I call it with my load case 2, these are my midplane strains. If I call it with load case 3, these are my midplane strains. Only load case 3 has a explicit shear load, so that comes as 007 here. Okay? So I made my computations a little bit more fancier. Now I'm able to compute midplane strains. But to compute a side-rule number, that is not sufficient. I need one more step. So I create objective function 3, copying the objective function 2 completely down here, and then renaming it 3, leaving the number of arguments same. I added one more line, Q bar, and Q bar is the Q bar matrices for the individual layers of a design by calling the Q bar matrix. So this now is going to compute the Q bar matrix of each design and output for the load case 1. It's a longer list that the Q bar matrix of the first design is here, and obviously Q bar of the second is the same. This is one design. Each layers, I think, is being evaluated here for the Q bar. What is it doing? This is Q bar design. I'm sending 1. This Q bar of first, Q bar of the second. So let me take one element of this. %1. Oops, I did the wrong thing. There's some noise coming from outside. %1. This is the Q bar of the first item in there. This is the first Q bar. Second one. What was the design that I'm sending in? This is what I'm sending in. Design that I'm sending in has 1, 2, 3, 4, 5, 6 layers of zeros. So Q bar of zeros are these 6. And the second design, initial limit 60 and minus 60, has these Q bar matrices. So everything is as expected. All right. Now, but that's not sufficient, because if I'm going to be doing my Saibu evaluation, I need the layer stresses. So I create a fourth objective function, which takes, I'm going to actually redo this from scratch so that I don't miss anything. So my fourth objective function, this one, is going to take the same thing, but it's going to also evaluate layer stresses. Okay, and layer stresses will be computed after Q bar by using Q bar and midplane. Okay. So this is fourth objective function. These are now stresses in the layers. And if I evaluate from my first design, did I not run this? I did. Oh, I need to call it with the lowercase. These are the ply level stresses for the first design. So you can see that the first 6 plies have the same stresses. Third one is plus 60 and minus 60. And then another plus 60, another plus 60, and another 0 and 0 here. So these are the different ply stresses. I am not done yet. I need to actually, just like in my test 2, I need to go all the way to Saifu number. So I'm going to copy this again and copy this. And paste it here and make it 5 and make it 5. And I'm going to add one more variable, which will come right after this. And that is going to require me to use, let me see. What do I need before calling Saibu? I have the Q bar matrices, stresses in the layers, and then I need the principal material stresses, which will mean that I will need the T matrix, okay? And I will add my T matrix here, transformation matrix. Or, yeah, and I'll compute it here. By calling it with the design. As opposed to only computing the zeros and plus minus 60s. I don't care, and I compute all of them. If you want, you can make it more efficient by adding a few additional things in here to streamline this, but this will be now computing the T matrix objective function of all the designs. And as you can see, the first 6 layers are these. So these are the T matrices. I'm going to take these 2 lines again. And make objective function 6. Objective function 6. I would add one more internal variable and one more computation for the internal variable. And that will be the principal material direction stresses in each layer. So that's a dot product of T matrix And I'm gonna copy that. Paste it. I'll call it stresses principal. Add it as my internal variable. And T matrix is here. Stresses layer Z are actually changed to this. That product of T matrix and the layer stresses. And I simplified it. This will be the new function, objective function 6, which will spit out it's spitting out something that I don't like. Where did I go wrong? T matrix is there, T matrix. Theta calculus. If theta, then T matrix is going to reach angles. So T matrix is correct. This is correct. Takes the design passed in here. Compute T matrix, that was correct. Then T mat is here. Dotted with layer stresses. Chop and simplify. There's something funny here. Primary level stresses shouldn't be ones and zeros. Do you see what I may have gone wrong in here? That's stress principle. Add it here. The matrix here. Dotted layer stresses. It's computed here. And I chop those and simplify again. Oh, I didn't execute it. Why didn't you tell me that I didn't execute this? I didn't execute this objective function definition 6. Now I did it. It's still not computing. All right, I'm baffled. Something is not right here because it looks like this thing has only 2. Something is not here right here, gentlemen. Are you following what I'm doing? My T matrix is computed. That's the design. That's this, which is fine. And all I'm doing is I'm taking this, without producting it with layer stresses. Let me see. Somebody has. Oh, okay. So I'm actually just checking this 5 minutes left and taking the dot product of the first components. And let me see if this works. Yes, it does. So it has to be a map. map. I'm dotting two matrices that are not in the same size. So principal material direction stresses will require map, thread, Tmat 1%1, and layer stresses, number 2. That's a dot product of these two operating on Tmat and layer stresses. Okay. So I'm taking a map thread, mapping it over key matrix and layer stress computation dotted like this. And I think I need to put this around it. And make it flatten, but before flattening it, let me see what it does. Yes, so it's going to compute the principal material direction stresses, and I need to use flatten, but not all of them. Let me see what it does if I don't actually use these brackets in here. No, it does require, let me see what it does if I put the ampersand here. Yes. So these are the principal material direction stresses. And the only other thing left in there to compute the Saibu number is basically, I think, called Saibu. And I do that by, what was the command for Saibu? Saibu failure. Saibu failure is this. Let me copy this. And I'm going to conclude it so that this will be complete for you guys. This is how we're going to be computing Saibu. But I'm going to create another objective function, which is the final. Hopefully. And I am going to add to this another and Saibu, and I'm going to put my Saibu computation in here. Actually, I don't even have to define this. So I'm going to put principal material stresses in here. These don't need to be there anymore. And little cases, this. And strength. Actually, I don't even have to define the whole case in there. The principal stresses is computed there. Only thing is strength, which is defined. And if I run the final version, I didn't do. Stress principle computed. Strength, is it defined? Defined. Saibu failure. Principal stresses are computed. It should be working, but let me see. Yeah, this is Saibu failure. There's alpha and beta stress principle. Why is there alpha and beta? This should work, but there's something strange in there. So let me stop here, and I'm going to send you this so that the Saibus are now computed. This last objective final should complete that, and you'll get the working version. I don't see why it's not doing it right now, but it's some simple thing that is not a big deal. But it will basically compute the Saibu numbers. So with this, you're going to be able to compute Saibu number as an objective function. And if you want to minimize or maximize this Saibu failure number, this will be what is going to be used. With that, I'm going to stop. And if you have any questions, I'll be here for a few seconds to see if I can actually make this thing working. If not, you can drop out because the lecture is over.